Hello and welcome back to question 6. Differentiation again, but this time we're doing power series. So in this question, we're given an equation. Can you show this? Now this question is quite kind in the sense that you just need to do implicit differentiation 2 times and just a tiny bit of manipulation, and then you can show what you're required to show. So let's get down to it. Using this equation that we're given, let's differentiate implicitly, then we get this one. And I guess this is a very common mistake made by students, and that is if you differentiate an exponential function, yes, of course you get back the same exponential function, but you must remember to differentiate the power. In this case, the power is not x, it's a function of x. So differentiating y, we get dy dx, and that is chain rule. Don't forget that. For the right hand side, it's a bit more straightforward. Differentiating a constant that's 0, differentiating this gives you a cosine x. So we got our first equation that contains our first derivative. Now differentiating again with respect to x implicitly. Now this time my left hand side would involve a product rule. So let's say we differentiate this, right? E to the y, that will give me e to the y and a dy dx. Combining with this dy dx here gives me a dy dx square. Now to get the second term, I fix this term and differentiate this one. Differentiating this, I get d square y dx square, so that's e to the y, d square y dx square. That's our product rule. On the right hand side, differentiating cosine, you get a negative sine x. Now just a tiny bit of manipulation, and that is, I'm going to substitute sine x. Sine x actually is equals to, using the equation that we're given, sine x equals to e to the y minus 2. So negative of that is negative e to the y plus 2. Okay, and then differentiating both sides by e to the y, that gives us really what we want to show on the left hand side, and then this thing over here, 2 minus e to the y divided by e to the y. I can write it as 2 separate terms, 2 over e to the y minus e to the y over e to the y, and that is exactly what we're required to show. Yeah, sorry about the sliding screen here. Now in part 2, the question says that, hey, if you take what you just gotten, which is our equation with the second derivative, differentiate it again, then can you show us what is the Maclaurin's expansion for y up to the term in x cubed? So up to the term x cubed means that we need the equation with the third derivative. So let's go ahead and differentiate again implicitly. So differentiating with respect to x one more time. Okay, this one's a bit more straightforward. Differentiating d square y dx square just gives us d cube y dx cube. Differentiating this, bring the power down, that's 2 times dy dx times the derivative of dy dx, which is d square y dx square. And then differentiating this one, maybe the negative one first, there's a constant, so that goes to 0. Differentiating this will give you exact same copy again of the same exponential function. Remember to differentiate the power, you get a negative dy dx. Okay, so now I have equations for my third derivative, second derivative, and first derivative, and also the equation given by the question. I'm going to substitute x equals to 0 into all of them to get my coefficients for my constant term, x squared, and x cubed terms in my Maclaurin series expansion. So let's start off with the first one, the one in orange, the first equation that we're given. Substituting x equals to 0, looking at the right hand side, sine of 0 is 0. So this is 2 plus 0. So e to the y is equals to 2. E to the y is equals to 2. I'm going to do a bit of adjustment over here because subsequently I need to state what is y equals to, or rather my coefficient for when x equals to 0, what is y equals to, that is natural log 2. But for the most part, to obtain the other coefficients, this one is more important. E to the y equals to 2. So once we have that, let's look at our white equation. Substituting x equals to 0, cosine 0 is 1. E to the y we found out earlier on is 2. So 2 dy dx equals to 1. Dy dx is equals to half. Yeah, dy dx is equals to half. Now let's look at the green equation over here. Starting with the right hand side, e to the negative y, that is 1 over 2. So this thing is just 2 times of 1 over 2 minus 1. So this is actually 1 minus 1. So the right hand side actually is 0. Looking at the left hand side, dy dx is equal to half. Half squared is 1/4. So d square y dx square plus 1/4 is equals to 0. So d squared y dx squared is negative 1/4 over here. And finally, let's look at the last equation. Again, starting with the right hand side. E to the negative y is a half, so this is negative 2 halves times dy dx, which is a half. So we have a negative half on the right hand side. Looking at the left hand side, this is 2 times our dy dx times d squared y dx squared, which is negative 1/4. So this is equals to negative 1/4. d cubed y dx cubed minus 1/4 equals to negative half. So that tells me d cubed y dx cubed is a negative 1/4. There you go. Now I have the coefficients of all my terms of my Maclaurin's expansion. Next, I just need to state it out. According to Maclaurin's expansion, y is equals to my first coefficient plus my second coefficient plus my third coefficient divided by 2 factorial plus my fourth coefficient divided by 3 factorial. Okay, and then if you simplify it out, this is what you get, and this is the answer for part 2. Now for part 3, we are supposed to use the MF26. Okay, so again, I just want to say that if you don't know your Maclaurin's expansion, don't worry, it's in the MF26. So in part 3, we're supposed to use the MF26, but to verify that this expansion will actually give us the answer we found in part 2. So we don't really have an expansion for this. First, I need to change it to y. To change it to y, I need to apply natural log on both sides. Okay, so y is equals to natural log 2 plus sine x. The common mistake made by students, I guess, is writing down this as y. Let me write it at the side here. Y equals to natural log 2 plus natural log sine x. This is not correct. Yeah, you need to take natural log of the whole thing. Okay. Next, you might be asking, oh, okay, if this is the case, then how do I do Maclaurin's expansion? Right? Because I kind of need natural log of 1 plus x. So what you can do is you can factor out the 2. Right, so let me erase this. There's some steps missing in between. Let me use purple, for example. This thing actually is equal to natural log of 2 times of 1 plus sine x over 2. I'm thinking, why do I want to do that? Because from the multiplicative law of log, that tells me that log of a times b equals to log a plus log b. So I can write it as natural log of 2 plus natural log of this thing, because it's 2 times this. A times b, a and b. Okay? Then the next thing is to actually think about this. You'll be thinking, hey, wait, I still can't do this. Well, you need to actually expand it out in terms of sine x. Sine x in the MF26 is equals to x minus x cubed over 3 factorial, so on and so forth. Okay? So that's x over 2 minus x cubed over 3 factorial divided by 2 again. Yeah? So that should give you x over 2 minus x cubed over 12. And then finally, I can treat this as x. Yeah? Then the Maclaurin's expansion for natural log is x minus x squared over 2 plus x cubed over 3. And this is the one that most students left out. Most students wrote x minus x squared over 2, but they forgot about this one. Okay? This one is important, the last one is important, because we will get an x cubed term if we take x over 2 and raise it to the power of 3. So don't forget about that. And then you should be able to verify, right? Simplifying and ignoring all the powers of x above 3, you'll get back the exact same thing that we found in part 2. And then we have verified our answer. So I hope this was helpful, and I'll see you in the next question.